That your IKEA bag, mate.
I have. It's cool. Very slight. I'm just trying to get into here.
Yes.
All right. We've moved that to.
How's that now?
There we are.
Yeah.
There's space for my bag. Make a space for my bag.
Yes, sir.
Piers, how was your sleep last night?
Well, it was too good because I didn't wake up. My recollection is I was looking at my mobile phone and then I woke up at 4 minutes past 9.
Plus 10?
No, 9.
Oh,
Or whatever.
I think last time.
And then I got here slowly.
It's alright, you got here.
Did you get your breakfast?
No. Well, yes. Oh, yes. Yes and no. I went in there, there was just some dry muesli there. So I stopped loads of dry muesli. And I thought, oh my God, what am I going to do? And then I went through the thing and I had to get a glass of water.
You just ate dry muesli.
Those of you that are here, we might as well start. So if you want to be quiet, it's with great pleasure that we have Neil Creamer here. He's flown over from Northern Ireland?
Northern Ireland, all the
Northern
way.
Ireland especially, because he was going to come last year, but for whatever reason, I can't quite remember, he didn't make it. But then I persuaded him to come this year. But he was particularly keen to come if he could discuss with you these ideas, which are based on the work of
Eric
Reiter. I mean, Neil will explain it all much better than I can.
Yeah.
Thank you, Neil.
Thanks, Lucy. Thanks for the opportunity to talk. So this isn't my own work. I'm here describing the work of Eric Reiter, and I apologise in advance that my understanding might not be 100%, but I hope it's good enough to answer any questions and to get across Eric's ideas. Sorry. Okay. Yeah, sure. I'm okay. Yeah. So that's the title is "Fixing the Error at the Heart of Quantum Mechanics." It's quite a bold claim.
Nice.
I was going to say something a bit less, but Eric wanted something a bit more bold. Start off. This is paraphrased something Bohr wrote after Einstein early on about the description of a photon. It's a wordy description about a beam split experiment, which basically says that if you fire a photon at a semi-reflecting mirror, it's going to go one way or the other and appear on one of two photographic plates you put behind the mirror. Or if you reconverge the photons, then they will interfere with each other like light. So this is already introducing this familiar thing called wave-particle duality. This is just another picture of the same situation. This is actually an illustration of what was in words there. It's a beam split experiment. It's showing light being shone at a semi-reflecting mirror being split, and a pair of detectors. The argument is that only one detector, I should say we need to be very careful about the words we use, because I'm talking about photons and I'm going to say in a while there's no such thing. So this is one of the tricks. I will probably trip over myself, and we do it all the time. There are all sorts of entities that have grown up around the way we see quantum mechanics that lead us to trap ourselves and talk in circles. So anyway, for now, let's talk about firing light. We say that the photon goes one way or the other. We've got two detectors here, and we see that it can appear at either, but not at both at the same time. It's a single photon. However, if we continued over time to fire light through the beam splitter, we'd get an interference pattern, which is a classic wave behaviour. By the way, there's a note at the bottom saying it's similar for matter. I'm going to come back to that later. the confusion when we talk about particles and waves is the idea of particles and waves is understood from the classical model. We've already talked about the Newtonian idea of a particle and the points, theoretical points, but one thing about a particle under the classical model is that it holds itself together. And the contrasting thing about a wave is that it spreads out. Something can't do both of those things at the same time. In quantum mechanics, a quantum mechanical particle is something that can do both of those things at the same time, which is what produces the headache that people like me had for years before we found explanations. The problem with that is that it's not an entity, it's actually a confusing self-contradictory concept. It can't be holding itself together and spreading. So I'm going to move straight on to Eric's experiment. This is a beam split coincidence detection experiment using a single gamma ray emitter. It's cadmium 109. The cadmium 109 emits one gamma at a time, not a photon but one gamma. Eric calls them an H-nu. He's not admitting to a particle idea, but it emits one at a time. In nuclear physics, a standard way of checking to see the emission rate of a radionuclide is to put it between two detectors. I hope that's clear enough that you can see that we've got a blue gamma source there, placed between two detectors, and the idea is if the source is emitting one gamma at a time, this is how they analyse nuclear decays. If it's analysing one at a time, it will show up on either one detector or the other, but not both. And then the time relationship between these pulses, you see there's a histogram there. It's a fairly level histogram. There's no relationship between one pulse and the other. The time difference between the pulses is completely random. There's a whole spread of time pulses between those things. There's no connection between those two events. Whereas if you were to put in a nuclide that emits two gammas at the same time, there would be a coincidence and you'd see something more like this. They would happen more often close together than far apart, so the time spread between them would describe a peak. Does that make sense? So, you know, they're occurring together. So this is how, this is what Eric did with his own cadmium 109 source in the first place, was to make sure that it produces this flat histogram, so there's no sense that there's any connection between one emission and the next. And then the experiment consists of, instead of having the source between two detectors, having a special custom-made thin detector and placing the gamma source on one side, so that any gamma coming out towards the detectors could hit one or the other, or both. There's the same electronics to detect the pulses. I should say a thing about, there's a lot more on this on Eric's site, but a reason why he chose gammas is because the relationship between the pulse height and the energy of the detection event is very clean for gammas. It's not for all wavelengths of light, and that introduces some confusion, makes it difficult to separate one pulse from another. Let me just go back. Can I go back, just back arrow?
Yeah,
Back arrow. I should say, there is, I discussed this with Eugene. He brought up the possibility that if you did get a gamma particle, like a gamma photon, it could hit the front detector, cause some event that then spat out another gamma photon which hit the rear detector. In order to rule out that possibility, what Eric did is to set the pulse height filter, knowing that that's tightly related to the energy, set that above half height. So you couldn't, if you had one photon came out and split its energy among two processes, it couldn't add up to more than one. So if you set the pulse detector above half height, two events would have to sum to more than one. The time frame window is really just doesn't impact on the result of the experiment, but the time was set so that the signal to noise of the experiment is as good as possible, but not so narrow that you wouldn't pick up enough events to get statistics. And of course there are background gammas in this frequency range, so the background was measured, the equipment was left for several hours to measure the background rate, which was found to be 5% of the detection event of the experiment. So what happened? What happened was that there were 15 to 20 times more coincidences from this experiment than were predicted by chance. So that means that within a certain time window, there were 2 pulses, 2 detection events, 15 to 20 times more often than would be predicted by the decay rate of the radionuclide allowing for background. And the question is why? Now this comes back to, Eric did this experiment after he'd done theoretical work, so now that we come back to the theoretical work, the question is, when you get a click at a detector in a quantum experiment, what is causing the click? This is Planck's second theory. I'm introducing something called Planck's second theory. I don't know if anybody's seen one of these things before. It's called a Pythagorean cup or a Tantalus cup. The idea is it's a glass with a siphon in the middle. You can fill it up so much, but if you fill it right to the top, it empties itself. You see what's happening there? Okay, so if you fill the glass, it empties itself. That's this is chosen as an analogy for the threshold effect that Planck was describing. If you consider this to be a system, whatever it is, an electron in an atom, if you like, or an atom, or whatever, a system, the loading theory suggests that it can absorb energy up to a certain level, and as opposed to the threshold being a minimum level below which a quantum event cannot occur, which is the usual interpretation, Planck's second theorem is that the threshold level is a maximum level above which the energy cannot go without causing a quantum event. So the argument here is that you could have preloading of this detector system, and that's why you wouldn't need a whole quantum of energy to trigger an event. So if you emitted an hν from the source in this experiment, it can propagate as a spherical wave, hit 2 points, 2 detector points, and cause 2 events. And that's one of the key mistakes we make and assumptions we make, is that an event at a detector is a particle. There's actually no justification for assuming that. It is tied into the photoelectric effect. That's how these detectors work. But the assumption that that detection event indicates that a particle arrived at the detector reinforces the idea that a particle came out of the source. And so that's so then you end up, okay, so that's a particle. Particle came out, it behaves as a wave in the middle, and then you've got 100 years of musing over how that happens. Whereas it doesn't. What emanates from the source is a wave. It propagates as light, it diffracts as light, it impinges on the detector, and then according to the state of the detector, there may or may not be an event, which is why you can't predict where these events will occur, but only statistically, because the statistics are actually illustrated in the diffraction pattern of the light as it propagates through the slits. The idea, just historically, this idea was originally suggested by Leonard. Planck described, he thought that emissions may be explosive, which is like a whole quantum comes out in one go, but that absorption may be continuous. And Millikan also referred to this as a loading theory, and Millikan was the last person to discuss this in the literature since about 1947. I don't think this has been in the literature loading theory. This is Eric's illustration, just sticking with the cup motif. I hope you can see there he's showing the two detectors, each with something in a cup, you know, whether that's an atom, an electron, or whatever you call it, that absorbs the energy, can be partly filled. And as the gamma ray impinges on it, it can fill and spill. And so that's why you're seeing events. That's another way of looking at what I just described in words there. A very important aspect of this is that energy is still h nu, but h is a property of matter, it's not a property of light. And that means, if going back to the photoelectric effect, I'll reinforce that in a minute with an equation, but it's not an energy effect, it's a frequency effect. And we know that in the photoelectric effect it is related to frequency. The argument has always been that it's to do with energy. However, if you don't need a full quantum, it wouldn't be to do with energy, because the energy is a full quantum. It could be related to frequency, and I think that ties in with the idea that's come up a few times this weekend, that it could be a resonant effect, and this is what Eric says. That absorption is resonant. Yeah, Eric there talks about free electrons being, he calls them charge mass, because if we're going to say that there's no such thing as a photon, and it's just energy, there can't be any such thing as an electron either, because the same rule applies. Yes, and I should say at the bottom, previous absorption, depending on whatever environment the detector is in, will set up preloaded states in the detector. You can't know what's going on in that detector. We don't know. It's very interesting that Jeremy mentioned over the weekend there's another piece of work supporting the EPR, the Einstein Rosen paper, that there are, talking about hidden variables which were supposedly falsified. However, in a very real sense, there are hidden variables in the state of the detector. We don't know the state of that detector, and that's what determines where something happens. This is the theoretical work that Eric did before he decided to do the experiments, and what he did was he looked at H, M and E. M is the mass of an electron, E is the charge of an electron. So those are constants that are used in all these equations to do with quantum mechanics, but they're constants. What he noticed is that there's no equation that doesn't have a constant on its own. They're all ratios. So every one of these, if you see well, we take the de Broglie equation at the top, we've got H over M as part of the de Broglie equation. Eric took that out and made it a factor. He calls it Q as a factor, H over M as a constant. Those things, if they vary together. They're always in parallel. The ratio between those things will always be the same. And that's why, looking at the photoelectric effect, which is the next one down, you can see that the determination of the photoelectric effect is to do with frequency, not to do with energy. Mu minus mu naught then. Now, I said something earlier about matter. Eric's also done experiments with helium nuclei. And he fired helium nuclei at a gold foil. Now, I'm going to say, this is Eric's experiment, and he argues that you couldn't be splitting a helium nucleus with the amount of energy that was available. So his argument here is it takes 14 MeV to split a helium nucleus, and he says there's only 5.5 MeV here. However, in light of the conversations that we've had this week, that may not necessarily be the case if there's a resonance situation. But nevertheless, his argument here is that he was getting two detection events from a single emission again with helium nuclei. But he's not the only one who's done that. This is another worker called Koch, that diagram on the left, I don't know if it's very easy to make out. They're actually, there's a helium wave produced there going through a slit. And you can see that part of it is going straight through, as you would expect particles to. And part of it is being diffracted, so as you would expect from a wave. And so part of that is focused in the middle. So what happened in that experiment is they were seeing, they were detecting as though there were particles going through and waves going through the same slit. The interpretation of this is that matter can have two states, and this is like a soliton wave. It can be a self-sustaining wave which holds itself together, or it can diffuse. I know there are lots of other theories. I have my own ideas. They're not Eric's, about waves and fluid dynamics that could be describing matter. But nevertheless, the argument from this is that the waves, when you talk about the experiment with matter, is the waves are the matter. The waves aren't the probability. The waves are actually the matter. The matter is a wave. It's not a non-physical entity that somehow influences an entirely different entity. It's the same stuff, but it's just behaving differently. So just to summarise that model, this is the threshold model at the bottom. Basically, light and matter both register as clicks at a detector. Both have only wave properties. The accumulation hypothesis or loading theory applies and explains why an event can be mistaken as a particle and how you can get more than one event from one emission. This is an advert for Eric. So this is Eric's website. I think if anybody's interested in digging into Eric's theory, I suggest they go along to his website. It's written far more than I could possibly even allude to here. And he's very open to communication. I have to say my hope would be that maybe next year Eric could come to the conference in the States and make a presentation himself on a wider sample of his work. Thank you very much. Yes?
Just a quick comment. It's like electromagnetic energy. I mean, electromagnetism is this continuous spectrum from radio waves down to light. Well, nobody talks about a radio particle. So, I mean, I never could understand the duality. I mean,
Isn't the wave an action another thing? I mean, it's usually something causes the wave. Like you wouldn't say a wave is in the sea an actual thing. It's water molecules being moved around by wind.
Well, this doesn't come from Eric. This is my own view and why I sympathise so much and I'm so happy to see Eric's work. Is that what you call a wave? A wave is something happening. It's a process. A particle is actually a process. Particles are dynamic. They're not static points under the same model. They're both the behaviours of the same thing, and the same thing is matter. Eric also talks about matter and light being separate. I don't agree with that personally myself, but I think these results are consistent with that. It's just matter doing different things. Matter is ether, is whatever you want to call it, naming it, giving lots of different names. It's the substance of which everything is made. Mm. Whether you call it matter, ether, the electromagnetic field, or Brian, whatever. Whatever you call it. Brian. Whatever you call it.
Been rambled.
Yeah, naming it explains nothing. It's just stuff. Eugene.
Yeah, well, firstly I have a short comment on one of your slides. You said that Eric considers free electrons as having a continuous spectrum, right? But that this is regular mainstream physics. It also says that free particles have continuous spectrum. So it's only the particles in potential wells that have quantized.
Yeah, I agree. I agree with that.
So it's yeah. But I also have a comment with regards to radio particles. They are actually considered as photons anyways. Even waves like 100 kilometers long are still considered to be one particle. But
because if you can do certain part of the spectrum, then you have to do the whole spectrum.
yeah, exactly. So anyways, but I have to refer to the general problem. Like the problem is actually serious with like quantum mechanical description of photon, because you see, the wave function in quantum mechanics is currently interpreted as amplitude of probability. So you have to take square of it, and you get the probability of a particle being here and there, etc. But for the photon, there is a big problem with such an approach, because you cannot interpret the wave function of a photon in such a way, because we know that photon is actually a wave. So it should have some size, you know, for the whole oscillation to come, the oscillation of E and B fields, etc. So, and it's a big problem. Like people have been trying to solve it for, I don't know, 70 years maybe at that moment, and it's still not solved. Like you cannot interpret wave function of a photon as an amplitude of a probability. It's just impossible.
I mean, that whole thing is why Schrödinger fell out with Born and Bohr, because of the idea that, I mean, Born's idea that you were talking about a probability was not what Schrödinger had in mind at all. He was envisaging matter. He thought it was a fluid dynamics problem.
So why was his cat about to die then?
Well, actually, after he fell out, he invented a cat to mock Born and Bohr. That was a joke. It's a very dry joke. But
I thought that was about probability. So
well, yeah, I think he was mocking the idea that it could be these probabilities could exist in these boxes, and not be a cat.
The funny thing, this was taken and against it.
yeah.
No, a complete different meaning.
Yeah, it's actually it's sort of fantastic now how it's being used as an illustration of quantum mechanics. No, that's not the point. It was meant to show how absurd it is. Well, now people say, look how absurd it is. You can't understand anything. Don't trust your intuition or your senses. Just listen to us. That's what they say.
Yeah.
Listen to what the politicians say.
Oh, well, yeah. Lee.
Yeah, there was a YouTube presenter who seems quite heated on the subject of photons, and he says there is no such thing.
Yeah.
But he says it's and these are his words, and I don't know if you've heard it all, if anyone else has heard this, but a coaxial field perturbation.
Isn't this the, I can't remember the guy's name, people would know him. No, it's the guy with all the tats who talks about Madison. Yeah, I can't remember his name. Theoria.
Professor Merrill will say that.
Very, very heated.
Yeah, but he says a lot of stuff that EU people would agree with. He's just got a very sweary, aggressive way. Yeah.
Neil, you can model it on a positron and electron. They oscillate between each other. The photon, I mean, they're locked as two vortices, and they oscillate each other. And when the proof for it is meant to be when it goes through a strong magnetic field and they become real particles, and you get an electron and a positron made from it. But they're there all the time, but they're virtual. They're kind of in the ether. That's where the photon, he argues that the photon doesn't exist as a separate particle.
Well,
I'll show you
I'm
the
arguing
derivation.
it doesn't exist as a particle at all,
I'll show
and
you the
nor would a
derivation.
positron or an electron for that matter.
Yeah.
I mean, the on ending is implies.
And the way it
particle.
rides on the top of
Yeah.
the oscillation between the two.
This is when the wave gets interrupted by something to create the matter.
Yes.
Yeah.
Yeah. It'll bring
It
it.
says, what is it that interrupts it to create the matter?
Well, the magnetic field, for example, a strong
Right.
magnetic field will create, bring into existence the positron and the electron, thus proving that it's a positron electron all the time. But it's not one or the other. And the positron could be argued to be the anti-gravity effect of the electron, so it means that gravity wouldn't bend it as well, because one's positive and one's negative.
But I think all those are assuming
They
particle.
exactly
You're assuming particle.
There's no particle with that.
Well,
It's,
I mean, just the on.
it's
That's
field
the
theoretical
problem.
model.
Yeah. When I talked about Eric was talking about, he calls it charged matter. It's very difficult because the nomenclature of a positron, electron imply particles,
That's right.
and then the matter, you're talking about the matter materialising out of somewhere.
The interruption between,
This is totally falsifying the idea that there is anything but matter. There isn't probability in matter. It's matter that is the waves.
Exactly.
A matter that we mistake for particles. It's just two different behaviours of the same, two of many different behaviours of the same thing.
So is that how you get E equals mc squared then? Because that's like energy and matter.
Well, mass.
Mass.
The M is
Oh,
mass.
okay.
Yes.
Yeah.
There's a confusion between mass and matter.
Yes, yeah.
Well, you're talking about mass being a
Yes.
C is
standing
the
wave,
speed of the
basically,
vortex.
right?
Sorry?
You're talking about mass being a standing wave.
That's the way it comes from.
I don't profess to know what mass is. I've got some ideas, but I think it's true that we don't really know what mass is. We don't really know what charge is. I've got ideas, my own ideas from fluid dynamics, but they're just my ideas, and I wouldn't even have any way to defend them.
Can you touch upon, you mentioned something which I'd love to hear your thoughts on, about if we come from the assumption that a photon does not exist as we understand it to be based on its properties or lack thereof, then it would likewise be assumed that the electron
Exactly.
doesn't exist, or perhaps even other particles, as we've spoken of. I'd love to hear you.
Well, this is exactly why Eric did his work. He started theoretically, and he wanted to do the work he hasn't done yet. That he wanted to do was with electrons. That proved to be practically the hardest thing to do. So he's worked with photons and helium nuclei. Just to say a thing about matter, there's an interesting thing about matter. When you talk about diffracting matter waves and detecting matter, there is an identity to that. It's when it arrives at the detector and does whatever it does, there is something there that by which you say it's a helium nucleus and it's not a chlorine atom or something. So there's an idea that there are wave packets. If you've ever seen a wave packet, it's basically there's what they call an envelope around a lot of mixed frequencies which contain a lot of information, and you'll see people talk about information. I don't really like the information idea, but there must be some difference between one matter wave and another if one of them looks like a helium nucleus and the other one looks like a chlorine atom.
Right, so how do we different? I love the matter wave. I've never heard that before.
Yeah, it's a quantum mechanical idea. The matter wave. The first equation I showed, the de Broglie equation, actually introduced the idea of matter waves. The top one there, the de Broglie equation, is actually saying that matter has a wavelength. I think conventionally it's assumed that matter is matter and it also has a wavelength. But this is saying no, matter's a wave.
Yeah, awesome.
I have a wave. I just wanted to venture the fact that when we find that the cause and the event are synchronicity or simultaneous or the same thing, I think it's possibly dangerous to continue to use the word matter. It's tangible, it's, I say visible in terms of detectable, so it's a tangible visibility, yes, but matter has all sorts of baggage down through the ages, so I just feel a bit wary of just charging off with matter.
Just to allude to another word that has so much baggage with it, it means something completely different to everybody, is God. Is another thing.
Absolutely.
People just bring along their own. They bring along their own understanding of the thing. So that's why I said whether you call it matter, ether, space-time, the electromagnetic continuum, whatever you call it, it's still the same thing. Our nature doesn't care what we call it. You know, it's there anyway. It's doing what it does.
Was it? I might have got a cross line here, but it's a wonderful thing of a self-contradictory concept that sets us off in spinning. Was that the previous lecture? But there was just this
You, a few slides
You.
before.
Oh, what I said about the,
Yeah, well,
the
we
wave,
ta- we take-
the wave
yes.
and
So
yeah,
we-
quantum mechanical particle.
So our naming gives us a self-contradictory
Yes.
concept that then splits out and sends us into
Exactly.
circular things.
That's
So
the,
naming, that's
the
why I
point.
say.
The reality isn't confusing. What's confusing is trying to explain our mistaken assumptions.
Yeah.
That's where we
It's a
get.
question of language.
That's where we get into trouble. Yeah.
I'm not arguing.
Can I say something?
Sorry, Piers.
Yeah, well, on that point, it is a question of language, because we're trying to describe nature in terms of everyday language of you know, meeting and greeting people, and of course there's limitations to that. But the first point I would make is that the problem with physicists is they believe their equipment, and you know, all the time we've got these problems. Now, what you said, and I think the idea of, well, when you talk about wave particles, okay, it's a wave in what? And then we're told a probability amplitude. And I remember as an undergraduate thinking, well, you know, I just don't get this. I mean, I've carried on using it, but a probability amplitude, and a wave in what? What is
Well,
this
I mean, I agree. I mean, this
well,
is
they
what.
had a supplementary, okay.
Sorry, you go ahead. That was
Okay,
your question.
that was just an aside.
Okay.
What I think is very important, what you said, is about the detector, because in undergraduate courses they talk very little about the detector. So, oh, the detector, that's it, it's given us the answer. But you've pointed out that, you know, the
That's the
detector has inside it all sorts of things. Now, you call them hidden variables. Now, I would say they're real hidden physical variables,
Yes.
but that's not the same as the hidden variables in quantum mechanics,
Well,
which are meant to be things we may or may not exist, which are deciding what you will see, which otherwise you thought was a random event. Right, but, okay, the point about the detector is obviously very important and means that physics should be retaught in terms of what you've just said. But it also means that the temperature of the detector will probably change the outcome, because if you make heated detectors, they're going to have lots more energy trying to jump out.
That's right.
And you might get 3, 4 or 5 particles for what you thought was just one event, if it's near critical. So, well, there's a suggestion. I wonder what your comments might be.
I agree totally, Piers. I had the same thought myself. Just because it's assumed that the photoelectric effect works the way we say it does, I don't think anybody's doing things
Well,
checking the
we
effect
should
of
make
temperature on
have a
this.
cold detector, a warm
Yeah.
detector, the same experiment in different
Eric
rooms.
said he actually has seen it.
You've seen this happen?
Temperature. Yeah, that's some of his other work. He has seen
Fantastic.
the effect of
All
temperature.
right.
Yeah.
But is it not a problem of creating a true vacuum or something? You can't create a truly neutral environment in which to test anything.
No, you can't.
I mean, look at the Sapphire.
Yeah.
You know, they thought they were creating a certain kind of environment, and
Yeah,
then
yeah,
they
yeah.
discover all these things they didn't put in themselves.
Well, it's when the anomalies come up, you
But it-
start to find out what's really going on.
If you could
or
pull
figure out
your
what's going on.
cool your detector to the lowest possible before it cracked or whatever, you know, like a liquid nitrogen, then you might get pretty good results.
You get probably different results
Well,
than you did
yeah.
around temperature. Yeah.
You might get a one for one instead of extra particles, you see what I mean?
Yeah. Yeah,
And
that's-
you could use that to calculate and see if that, well, calculate properties of the detector and see if that's consistent with it.
Yeah. Yes, definitely.
But all this thing about detectors again, it deals with, well, we got this thing in quantum mechanics, oh yes, it depends on the observer, but oh, hang on, this is idealistic nonsense in my opinion, because a detector as an observer, you can go in another room,
Yeah,
not be
that's-
there, you're
that's
not,
a- that's
the
a
idea of a
ridiculous
person
leap,
being
yeah.
involved is
Yeah.
a nonsense. It's a question of a physical interaction
Yes.
going on, upsetting what would otherwise happen if there was not a physical interaction going on.
I think there's a more general point actually, just extending what you've said, is that you can't know anything about light unless you stick an atom in the way.
Yes, exactly.
And
that's-
then
that
to
is
mi-
the interference.
And then
It's not
to
you
mistake
watching.
what the atom does for some property of light is what this is all about.
Exactly.
Yeah.
Exactly. Oh, well, I'm going to give a round of applause for that.
Neil, are they all time independent equations really then?
They are.
Yeah, because if when going back to longitudinal component we were talking about before, that's a time dependent, isn't it? So it absorbs it over, it allows for absorption up to the top of the cup.
Yes,
See what I mean?
that's a very interesting thing. This is something I haven't talked about here.
This is
one of
where
the,
this
one
is-
of papers
going
by
in there.
James, I think it was in the 20s,
Mm.
was it the last serious paper about the photoelectric effect showed that there's a time dependence.
You have
It's
to
not,
drive it
it's
with
not
time.
it's always, you're always told it's instantaneous.
No,
and it
you can
couldn't happen
drive it with
classically.
time, can't you?
Yeah.
You
Yeah,
can,
it's-
you can
it
pull
is-
up with different.
Well,
It
there
is
is
a
a delay
very,
involved in
very
filling up.
fast, time-dependent process.
So what is the delay? I mean, nanoseconds, nanoseconds?
I don't know. I should think it would be a shorter time scale than that.
But if it's a cold surface, it would take longer probably.
Yes.
Well, there's a whole lot of experiments
There's a lot of preloading.
should have
you
been
see.
done. Why weren't they done? Why weren't these experiments
temperature is
done
going to affect the
50 years ago?
preloading.
What's wrong with you people?
Appears there has been an experiment done, it was reported just in the last month or two, which has shown that
Why not 50 years ago?
there is a time delay. I suppose because of the difficulty of measuring it.
Okay, and what how
Because there
much
was
is
a time
that
delay.
typically?
I don't know, I
Well,
don't
I'll
know
have
the
to get
details. It was just significant that they had found that it was a cumulative effect and not something
Fantastic.
instantaneous.
Fantastic.
Hey!
There you go. So, Eric, I don't know if Harry knows about that. I'll have to get that.
Oh,
for
it
him.
was very recent. I've
Yeah.
got it on my computer, I think.
Yeah. Well, there you go. And with
Brilliant.
Yeah.
Yes. There you go. So that's it. Well, because we can't know everything about the detector, is why we can't know when we're going to see an event.
Well, this question, of course, puzzled me very much about the ether very early on. And it was a radiation physicist back in the 70s who gave me a clue, but I won't talk about it now because I understand I'm on at 3 o'clock. And it's significant in biological terms as well. So.
Okay.
Mm.
Thanks very much. Well, thank you very much. Thanks
thank
for your
you.
attention. Thanks for listening.
Right, if you want to stretch your legs for a minute while we just thank you very much. Set up for Eugene's. That'll be on in 5 minutes.
Oh, sure, yeah. Yeah, I mean, this is how I was trying to do it.